Welcome to This Explainer. Today, we're diving into what I think is a truly massive shift in math education. We're talking about moving students away from those rote, arbitrary math rules we all grew up with, and instead guiding them toward deep, conceptual sense-making. For the longest time, math has basically been taught as just a rigid series of steps to memorize. But what actually happens when we ask students to make sense of the math they're doing? Well, let's jump in and find out. Okay, let's kick things off with a little thought experiment to crack the classic mystery of dividing by zero. What happens when you try to share 5 oranges with 0 children? I mean, it sounds completely absurd, right? But think about it. Often students are just told, hey, division by zero is not allowed, end of story. Or they end up harboring this misconception that the answer should just be zero, or maybe the number 5 itself. But when we pose a seemingly silly physical question like this, it forces us to step back. It forces us to use real-world reasoning instead of just regurgitating a hollow rule. So if we take those 5 oranges and try to work backward, well, division is just the inverse of multiplication, right? So we have to ask, what number multiplied by 0 equals 5? And, as we all know, there is absolutely no answer. No number times 0 can ever equal 5. By taking a proposed answer and plugging it back into a multiplication problem to check it, we aren't just handing students an arbitrary rule to blindly follow. We're actually using meaning to prove why the rule exists in the very first place. So now that we've used meaning to bust that old arbitrary rule of 0, here's our roadmap for the rest of this explainer. We just covered the division by 0 mystery, and next we'll look at decoding contextual word problems, avoiding the dreaded keyword trap, mastering multi-step problems, and finally fixing common student errors. All right, let's move right into section 1, decoding contextual word problems. So picture this. Imagine a student just totally freezing up at this incredibly daunting dirt truck problem. 638 truckloads of dirt. The average truck carried 6¼ cubic yards of dirt, which weighed 7.3 tons. How many tons of dirt were used? I mean, when you mix huge numbers, fractions, and decimals all into one single paragraph, it's literally enough to paralyze anyone. Faced with this, students usually have a really hard time figuring out the right operation. Honestly, sometimes out of sheer panic, they'll just grab 2 random numbers from the text and take a wild guess at what to do with them. But here's where it gets cool. Instead of trying to mentally juggle 638 trucks and 7.3 tons, we can unlock the whole problem just by substituting smaller, friendlier whole numbers. What if, actually, scratch that, let's just pretend we only have 7 trucks and each one carries 4 tons. Suddenly, boom, the student can draw circles for the trucks, put 4 dots in each one, and they can actually visualize the math without getting totally lost in the weeds. They can easily see that 7 times 4 is 28, and then they just apply that exact same operation, multiplication, right back to the original unwieldy numbers. It's a total game changer. Which leads us to a highly structured, almost foolproof methodology for decoding complex data, the simpler problem strategy. It's 6 steps. First, substitute small whole numbers. Second, model the problem using those friendly numbers. Third, write an equation for the simple version. Fourth, write the corresponding equation but pop the original numbers back in. Fifth, do the math, calculate. And finally, step 6, write the answer out in a complete sentence and literally ask yourself, wait, does this actually make sense? Okay, moving right along to section 2, the keyword trap. We really need to talk about this because the keyword strategy is kind of a false friend. The myth tells students to just skim a word problem, hunting for magic phrases like in all or left over as this easy shortcut to figure out the operation. But a true meaning-based approach that requires students to actually read for the structure of the story to make sense of the situation. Math is all about reasoning, right? Sense-making strategies will always work for you, whereas keywords are basically guaranteed to mislead you eventually. Let me show you exactly what I mean with a quick example. There are 3 boxes of chicken nuggets. Each box contains 6 nuggets. How many nuggets are there in all? Now, if a student was taught the keyword myth, that phrase in all might trigger them to instantly guess addition. They see in all, they grab the 3 and the 6, add them up to get 9, and they just move on. But by doing that, they are completely missing the structural reality of the problem. It's 3 groups of 6, it's multiplication. If we let students rely on keywords, we're basically setting them up to fail the second reading comprehension and multi-step logic enter the picture. Which perfectly tees up section 3, mastering multi-step problems. You know, if single-step problems are tricky, multi-step problems can feel like hitting an absolute brick wall. But we can actually turn a frustrating multi-step problem into a really engaging mystery. We do this by framing the student as a detective who's searching for the hidden question. This is the unstated intermediate step in a problem. And here's the catch. It has to be identified, and it has to be solved before you can ever hope to arrive at the final answer. Let's look at how we actually train students to find these questions. First, you ask them a single step. Toby bought 3 dozen eggs for 89 cents a dozen. What's the total cost? Easy enough, right? Once they solve that, you give them step 2. How much change did Toby get back from a $5 bill? Simple subtraction. Finally, you present the combined multi-step problem. Toby bought 3 dozen eggs at 89 cents a dozen. How much change from $5? The crucial takeaway here is teaching students to link those ideas. They have to find that hidden cost of the eggs, that unstated question, before they can even touch the final change calculation. All right, bringing us to our final section, Section 4, Fixing Common Student Errors. When students make mistakes, it's honestly fantastic because it gives us a direct window into their mathematical thinking. For example, say a student sees absolutely no relationship between addition and subtraction. Instead of just drilling them with boring rote fact families, have them literally act out problems using the same 3 numbers so they can physically see that part-whole relationship. Or what about that stubborn misconception that the divisor always has to be less than the dividend? Break that rigid rule. Ask them to find a way to share 3 cookies with 5 friends. They'll figure out real quick that you absolutely can divide a smaller number by a larger one. It just gives you fractions. And what if a student writes the wrong division equation entirely? Like they write down 5 divided by 120 when they actually meant 120 divided by 5. Just ask them to create a real-world story that matches their equation. Seriously, imagine trying to write a story about sharing 5 single items equally among 120 people. It instantly exposes how absurd the error is. Or going back to the beginning, if they think division by 0 equals 0, hand them 5 blocks and tell them to physically make sets of 0. They'll realize in about 2 seconds that it's just literally impossible. So, as we wrap up this explainer, I really want to leave you with a question to chew on. Which arbitrary math rule are you going to replace with a sense-making strategy tomorrow? Whether it's swapping out that superficial keyword hunt for analyzing story structure or replacing rote memorization with hands-on physical modeling, the shift from mechanical steps to true, deep mathematical meaning always starts with just a single strategy. By focusing on meaning, we empower students to truly understand the math they're doing. Thanks so much for joining me today on this journey into mathematical sense-making.